Hi everyone, welcome to the paper presentation for throughput prediction on 60 GHz mobile devices for high bandwidth latency sensitive applications. My name is Shivang Aggarwal and this was a joint work in collaboration with Zhaoning and Charlie from Purdue and Moinak and Dimitrios from Northeastern. So high bandwidth latency sensitive applications like live 4K video streaming, virtual reality place extremely high demands from their underlying networks. And since we're talking about mobile devices here, these demands need to be met wirelessly. So IEEE 822.11ad, which is the standard that governs the use of the 14 gigahertz of unlicensed spectrum around the 60 gigahertz frequency, promises data rates of up to 6.7 Gbps, making it one of the prime candidates to enable those applications wirelessly. Now, the first smartphones with these technologies were released in 2019. However, being at such high frequencies, there are certain challenges. For example, with mobility and blockage, there are extremely large throughput variations. And most applications today have some sort of quality adaptation built in to deal with these throughput fluctuations. For example, adaptive bitrate streaming monitors its network conditions, and based on that, it adapts the content quality to optimize the user's quality of experience. Now, let's focus in on this first step here. So, what happens here is basically ABR looks at its past network conditions to try to estimate or predict the throughput in the next time interval. And this problem has been studied extensively in the sub 6 gigahertz networks such as legacy Wi-Fi and cellular networks. However, for 60 gigahertz wireless LAN, that's not the case. And we'd also like to point out another thing that due to the unique propagation characteristics at 60 gigahertz, this problem becomes even more challenging. So in this work, we performed the first measurement study of the throughput predictability in 60 gigahertz wireless LAN using machine learning. Now, to conduct this measurement study, we were faced with a couple of challenges. The first one was with regards to data collection. Now, to reliably train and test any machine learning model, we need large amounts of data. So, to collect this large amounts of data, we used a programmable three-axis motion controller, which is typically used by professional photographers. And using this setup, we were able to collect more than 100 hours of data, running different applications and performing random realistic mobility patterns. And we make this entire dataset publicly available at the following link. The second challenge is with regards to the machine learning model. So we know that previous works have looked at prediction timescales in the order of a few seconds. However, in this work, we look at timescales as low as 10 ms to deal with applications such as VR. So we need our model to be highly accurate, but at the same time be lightweight enough so as to be run on mobile devices. So what we did was we started with two neural network models, one from a previous work and another which is known to be appropriate for time series data. And for each model, we performed a grid search to arrive at the smallest configuration that strikes this balance. And using this approach, we were able to come up with these three models. As inputs to these models, we gave the pass throughput, the pose information from the phone sensors, and 60 gigahertz link information from the driver. Now coming to the results, starting with the static scenarios, here we plot for the different time scales of predictions from 10 ms to 2 seconds, what was the root mean square error for our three models. And the first observation we make here is that for as the timescales become coarser and coarser, the accuracy of our models improves. And in general, even across all timescales, we believe that the models do make reasonable enough accurate predictions. And for example, at the 10 ms timescale where the models perform the worst, we found that 78% of our predictions were within 10% of the actual throughput. Now, coming to mobile scenarios, we again notice the same trend that as the timescales become closer, the accuracy of the models improves. However, in general, these models do perform worse than how they were performing in the static scenarios. We also found this presence of a sweet spot at 400 ms, after which and before which the model's performance becomes worse. And this leads us to believe that there is an interesting trade-off between the length of the history window and prediction window in the case of mobile scenarios. Now, we also wanted to understand how much each feature contributes to the model's accuracy. And so here we show you the most important and least important features in for all the timescales for both static and mobile scenarios. And as you can see, for the coarser timescales, MCS and throughput are the most important and least important feature respectively in both static and mobile scenarios. While for the finer timescales, this is reversed, with throughput becoming the most important feature and MCS becoming the least important features in some of the cases. Now, we also perform experiments with a couple of application scenarios. So, first is VR, where we need predictions at the 16 ms timescale, and second is ABR video streaming, where we need predictions at the 2-second timescale. Now, with VR, we found that the RMSE of our three models was around 160 Mbps, while with ABR, that drops to 115 Mbps, and with 15% more predictions within the 10% margin. And so for VR, we say that it can benefit from throughput prediction, but only if the predictions are used conservatively and the applications can tolerate a certain margin of error. While in the ABR case, these applications can use these predictions with much more confidence, thus ensuring a high user QoE. Now, since one thing I mentioned before was that we wanted our models to be lightweight enough to be run on mobile devices. And so to evaluate that, we basically ran the three models on the ROG phone to smartphone, and we measured the inference delay and the memory consumption for the three models. So basically what we found was that for the BP8 model, the inference delay is less than half a millisecond, which means that it can be run for any time scale, while the RNN models take 2 to 4 ms to make their predictions. Thus, they can only be used for the more coarser time scales. We also noticed that memory consumption for all the three models is negligible. So in conclusion, we presented the first measurement study of the throughput predictability on 1180 enabled mobile devices. We showed that throughput can indeed be predicted well using small neural networks. We also showed that for coarser timescales, scale throughput history hurts, which suggests that at those timescales, we should probably limit the history window used. We also found that for different timescales, different sets of features give the best prediction accuracy, thus suggesting that the models need to adapt a set of features that they use based on the application they're predicting throughput for. And that's all from my side. Thank you so much for listening. The dataset is available at the following link, and please feel free to email me with any questions. Thank you.